Hello everyone, I am Siddharthan. Currently, we are in the seventh module of our hands-on machine learning course, and this seventh module is all about building machine learning models from scratch. In my previous videos, I have explained you what is the intuition and math behind a support vector machine classifier, and we have also discussed about the loss function for a SVM classifier. So in today's video, we are going to discuss what is the gradient descent for support vector machine classifier and what are the different formulas that we have for gradients for a SVM classifier. So this will be the agenda for today's video. So I will be giving you a quick recap of what we have discussed about support vector machine and so far, and after that we can go in detail about this gradient descent and what are the gradients formula for support vector machine. Okay, so let's get started. So we have already discussed that a support vector machine model is used in both classification as well as regression problems, but it is predominantly used in a classification problem, and that too a binary classification problem where the model will try to classify the data points into two groups. If you see this diagram, we have two kinds of data points. So one group of data points is represented as blue colored circles and the other group of data points is represented as red colored squares. So if you use a support vector machine classifier, it will try to classify these data points into groups as we have. So how it basically works is it will try to create a hyperplane. So you can see this black colored line here. So this line is called as hyperplane, and this hyperplane separates these two types of data points. Okay, and there is another important term that we have in support vector machine classifiers, and that is support vectors. So you can see this data points. So these two blue colored circles and these three red colored squares. So these are the data points which lie closer to this hyperplane, and these are called as the support vectors. So the data points in a data set that lies closer to the hyperplane are called as support vectors, and if the position of this support vector changes, the position of the hyperplane also changes. So the position of the hyperplane basically depends upon the position of the support vectors. Okay, and if you draw a dotted line along these support vectors in both sides, this particular region is called as the margin, and your hyperplane lies exactly in the middle of this margin. Okay, so these three are the important terms when it comes to a SVM classifier, and this margin should be as long as possible. So if you have a greater margin distance, that means your hyperplane can correctly segregate the data points. So it can clearly define some segregation between the data points. If the margin distance is low, then it means that the hyperplane does not know a clear distinction between these two data points. So we always try to increase this margin space. Okay, so that's one of the main thing about support vector machine classifier. So once we train this SVM classifier, if you give a new data point, it will try to see in which side of the hyperplane the new data point is coming. So once it realizes it, it can classify whether that point belongs to the first group of data points or the second group of data points. So we have discussed how the SVM classifier mathematically finds this in our mathematical intuition videos. I hope you have watched that one. So if you haven't watched those videos, you should surely check out that. So I'll give the link for those videos in this particular video description, so check that out. So this is how a support vector machine classifier can find among which groups a new data point lies. Okay, so this is the basic intuition of a SVM classifier, and mathematically, so these are the important formulas that we have. So let's say that we have two groups of data points here. So one group of data points is represented as red colored circles, and then the other group is green colored circles, and these are the equations of the lines that we have. So this blue color line is our hyperplane, and this is the equation of our line where W and B is our parameters of this line. So W is basically the weight and B is the bias. So these two are the model parameters. So the parameters of our SVM classifier, and this is nothing but this is similar to the equation of a line, which is y is equal to mx plus c. Okay, and these two are the equations of this margin lines. So if you take this distance x1 minus x2, so this is your margin distance, and if you want to find this distance, you can easily subtract this green colored equation and red colored equation. So when you do that, you can find this particular distance, and this distance is given by this factor. Okay, so we will basically try to increase this margin size. So 2 divided by norm of W is what is the margin distance. So I have explained you how we derived this particular formula or function in my mathematical intuition video. So this is our margin distance. So we always try to maximize this margin distance, so there is a clear distinction or clear segregation between the two groups of data that we have. Okay, and this y I cap is our label. So here the label will be either -1 or +1. So if the model tries to multiply the input factor with our weight and bias, so it basically tries to multiply it with weight and add some bias to it, and it will try to find the value, whether the value is greater than -1 or it is sorry, whether the value is less than -1 or it is greater than +1. So these are the two possibilities. If the value is less than -1, in that case we take the label value as -1, and if the value is +1, and the label value will be +1. So these are the two labels that we have. So the model will try to find this label value, and this is how it segregates these two data points. Okay, so these are the two groups of data points that we have. So this is how this is the mathematical intuition of a SVM classifier. And also we have discussed about the loss function, right? So we know that the loss function for a SVM is a Hinge loss. So Hinge loss is given by this particular equation. So I have explained this in my previous video. So basically it is represented as maximum of 0, 1 minus yi of W transpose Xi plus B. So this W transpose Xi plus B is nothing but your Yi cap. So the label that you are predicting. Okay. So we have already discussed about this definitions and all in my previous video. I'll just explain you about this particular formula. So we take the value, first term value as 0 when the model makes correct classification. If the model makes wrong classification, the value will be 1. So these are the two values which we should choose from for this first term. So if the model makes correct prediction, the value is 0. If it makes wrong prediction, the value is 1, and then we will subtract this term from this value, either 0 or 1. So basically what we get is, if the model make wrong prediction, then the loss function value will be higher. If the model makes correct prediction, then the loss function value will be minimum. So we basically will try to minimize our loss function value. So a low loss function value basically tells you that your model is making almost correct predictions. Okay, so we have discussed about this graph and all these definitions in my previous video. I don't want to go into that again. So this is the Hinge loss. So this loss function is very important for us in order to build our gradient descent algorithm. Okay, so now let's discuss about the gradient descent that we have. So when we build a gradient descent, we will try to plot between the cost function and the weight and bias of the model. Okay, so basically the loss function is when you compare the true value and the predicted value of one particular data point. So we will try to find that difference, and that difference is your loss function. So that is what basically loss function means. So we will try to compare the value of the true value and the estimated value. So what is the difference between them? So when you do that for the entire data points, so let's say that we have 500 data points. If you try to find the true value and the predicted value for all these 500 data points separately, then each of this value is called as loss function. When you try to find that particular difference for the entire data set, so the true value and the predicted value for this entire data set, and you take a score, and that will be your cost function. So cost function is basically the average of all the loss function for all the data points that you have. Okay, so cost function is the parameter that we need in order to build this gradient descent. So here we will take cost function in our y-axis and weight in our x-axis. So these are the two axes that we have. So the idea of gradient descent is to find the best parameters. So here the parameters are nothing but weight and bias. So how we do that is, so basically if you have a minimum cost function, that means your true value is close to your predicted value. So that means your model is making almost accurate prediction. If your cost function is I, that means there is a huge difference between the true value and the value predicted by your model. So our ultimate goal is to reduce this cost function. Okay, and how we will do that is, we will try to change the value of weight and bias. So we will try to change the value of these parameters, and at each step we will try to find the cost function. Okay, so we will initially or we will randomly initialize some value for our weight. Okay, so let's say this is a random initial value for our weight, and for this particular weight value, let's say that the cost function at this point, so this means the cost function is I, right? Because this point lies in the top region of this cost function y-axis. So we can say that here in this case the cost function is very high. So we need to reach to this particular point. So at this point, if you just come to the corresponding y-axis value, it will be very less, right? So at this point the cost function value is very minimum. So this point is called as your global minimum point. So if you take the weight value at this global minimum, you will get a minimum cost function. Okay, so we need to reach to this point from this point. So we will randomly initialize some value for our weight, and we will constantly change this weight value in order to minimize this cost function. So this is the idea behind the gradient descent, and gradient descent is one of the most important optimization algorithms we have in machine learning. Okay, so we have discussed a lot of times about gradient descent. I hope you are very thorough with gradient descent as of now. Okay, so we will try to regularly change this weight value, and we will try to minimize this cost function at each step. So this is how gradient descent works. It will try to add some change to our weight value and bias value so that the cost function changes. So this is the basic working of a gradient descent. And how this gradient descent does this is basically by using derivatives. So it will try to differentiate the cost function with respect to weight and bias, and this is how it can minimize this cost function. Okay, so this is the mathematical aspect of gradient descent. And this, when you plot this cost function and weight, you will get a curve like this, a u-shaped curve like this, or you can call this as a convex curve. Okay, so the idea is to, like, wherever you are at initially, so initially you may have a higher weight value. In that case, it might be at this point. So wherever you start at this curve, you have to reach this global minimum. Okay, so that's the idea of gradient descent. So no matter what is the weight value, it will end up at this particular global minimum. Okay, so here we have plotted for cost function and weight. Okay, so it is a two-dimensional structure, and if you do this for both weight and bias, so we know that the two parameters that we have for SVM classifier is the weight and bias. And if you try to change both this weight and bias value and compare it with this cost function, you will get a three-shaped curve like this. So this is just a representation. So we basically try to change the weight value and bias value repeatedly so that we get a minimum cost function. So we will, if a particular weight value and bias value as a minimum cost function, so that will be our global minimum, and that will be our optimum parameters. Okay, so our goal is to get this optimum parameters values. Okay, so this is how the definition for gradient descent looks like, and this is the formula for gradient descent. Let's try to understand this. Gradient descent is an optimization algorithm used for minimizing the cost function in various machine learning algorithms. It is used for updating the parameters of the learning model. So we have already used this gradient descent in our linear regression and as well as our logistic regression. Now we will be using this in our SVM classifier. Okay, so it is an optimization algorithm. Optimization in the sense it will try to improve the efficiency or the accuracy of our SVM classifier model. And how does it does is by basically updating your parameters of the learning model. Parameters is nothing but your weight value and your bias value. So this is how the formula for gradient descent looks like. So W2 is your updated weight, new weight, and W1 is the previous weight. So updated weight is equal to previous weight minus learning rate into djw by db. So let's try to understand what does all these terms mean. So basically W is your weight and B is your bias, we know that, and L is your learning rate. So learning rate is nothing but how much change do you want to give to your weight and bias. Okay, so I'll just go to my previous slide. So we know that we will randomly initialize this weight value, right, and we will change our weight value. So this is our changed weight value, right. So learning rate is nothing but how much change do you want to give to your weight or bias. Okay, so it is basically the magnitude of change that we are giving to our parameters. So we will try to give some change to your weight regularly, right. So this is your learning rate value. So that is represented by this L, and dj by dw is the partial derivative of cost function with respect to weight. So that is given by this dj by dw, and dj by db is partial derivative of cost function with respect to b. So what does this basically say is, so dj by dw represents how much your cost function changes when your weight changes. Okay, so that is represented by this term, and dj by db basically represents how much your cost function changes when you change your bias. Okay, so if you come to this graph again, so we are changing the weight value, right. So the weight value changes from this point to this point. So this is the change in the weight, and for that you will try to find what is the change in the cost function. So this particular part, so we will try to find that value. So for change of weight for this magnitude, the change of cost function is this. So we will try to take the derivative of this, and that is represented by dj by dw. And if we do that in terms of bias, it is called as dj by db. So this is the partial derivative of cost function with respect to w and with b. So this formula for gradient descent won't change. So only the formula for dj by dw only. So this is called as gradient. So you can call this as either gradients or derivatives. Okay, so this gradients value changes for different models. So we need to understand what is the formula for this, and this is the formula for updating the weights. So as I've told you before, W2 is your updated weight, W1 is our previous weight, and B2 is your updated bias, and B1 is your previous bias. Okay, so this is the formula for updating the weights, and these two are dj by dw and dj by db are your gradients formula. Okay, and let's now try to understand what is the formula for these two terms. So when we think about gradients for SVM classifier, there are two conditions. So first condition says if yi into wx plus b is greater than or equal to 1. So we know that w is our weight, x is our input feature, okay, and b is your bias. So in our data set we have input feature, or we can say this as the column. So we have multiple columns in our data set, right? So this will be our input feature. So we will try to find this value and we will multiply it with this yi. So yi is nothing but your label. If this value is greater than 1, we have different formulas. If or else in other condition where the value is less than 1, in that case we have different formulas for our derivatives, okay. So these are the two formulas. So when we have this kind of a condition, we get the dj by dw value as 2 lambda w, and your dj by db value will be basically 0. When this condition is not satisfied, we have the other condition. So in this case the formula will be dj by dw is equal to 2 lambda w minus yi xi, and dj by db is equal to yi. So this is the formula that you get. So how you basically get this formula is we need to differentiate this particular. So this is our Hinge loss, right? So we need to differentiate this particular equation, particular formula in terms of weight, and then with in terms of bias. So that's what we have to do, and when you do that you will get the formula like this. Okay, so these so we don't have to go in detail about the derivations and all, so that's not required right now, but we need this formulas alone. Okay, so these are the two conditions that we have and the formula in each condition. And once we find these formulas, we will be using this in our updating weight formulas. So you will substitute this particular formula in this, and when you do that you can find the optimum parameters. So these are this is how the gradient descent works for a support vector machine classifier, and these are the formula for your gradients when it comes to a support vector machine classifier. Okay, so in my next video, let's try to build this support vector machine classifier from scratch in Python. So in that case we will be using all these formulas. So all this updating the weight formulas and all the gradient formulas and all, we may use a different form of this particular formulas. We may not use the same format, we may use the different formulas. So let's discuss about that in later, but this is the theoretical aspect of these gradients, and this is how the formula looks like. Okay, so actually I have to explain one more thing. So we have a new variable called as this lambda, right? So this lambda is basically called as lambda parameter, and the real name for this lambda parameter is the regularization parameter. So what this regularization parameter basically does is it will try to give some importance to the misclassified data points. Let's say that we have trained our SVM classifier, and our support vector machine classifier sometimes can make mistakes, it can make wrong classifications. Okay, so we know that it classifies between two groups, right? So it may make some misclassification, and this regularization parameter will try to give some importance to our misclassification. So the final goal that we want, or the final objective that we want with our SVM classifier, is that we should have a maximum margin and we should have a minimum misclassifications. Okay, so we know that the margin distance should be greater when it comes to a SVM classifier, and we should not make any misclassification. So that is given by this regularization parameter, which is represented by lambda, and this is why this lambda comes into play when we use a gradient descent formula. Okay, so that is the importance of this. And when we build our model, we will manually give some value. So we will give some value for our learning rate as well. So for learning rate as well as this lambda parameter, we can manually assign some values. So that is all about this gradients formula, and I hope everyone is clear up to this point. If you don't understand how we arrive at this formulas and all, it's not problem. So in my next video, let's understand in detail about how we can build this from scratch in Python. Okay, so that's it from my side for this particular video, and I'll see you in the next upload. Thanks for watching.